In this video, we'll be looking at functions. Specifically, we will define what a function is, look at how we can visualize functions, and then define several operations that can be performed on functions. So first, a function is a correspondence between two sets such that each element in the first set has a corresponding element in the second set. Furthermore, this corresponding element is unique, meaning that's the only element that corresponds to this first element. Now, typically, we'll represent a function this way. So this here denotes the function. So in this case, we're going to define the function with f. This is the first set. And that would be the second set. So for this, our function is f. The first set is a, and the second set is b. Now this first set, so in this example, a, is called the domain of the function. And the second set in this case up here, b, is called the range of the function. Now there are two ways in which we can visualize a function. First is to visualize it as a machine, and the second is to visualize it as a mapping. So in the machine visualization, what we wind up with is the input is what can go in the machine. In other words, it's what the machine can accept. These are the raw materials of the machine. The function itself is how the machine processes the input. And the output is what comes out of the machine. Or it's the processed materials. So in this image right up here, this machine, the machine cuts fruit in half. In this particular function, it's only apples, so it's cutting apples in half. So the input would be the apples. The function itself is cutting the apple in half, and the output would be the halves of the apple. In the mapping visualization, each element of the domain is mapped to an element in the range. So in this mapping here, the domain would be the four shapes that we see, along with the associated color, right? So we have red triangle, yellow rectangle, green Pac-Man sort of thing, and a red square. The range are the colors red, blue, green, purple, and yellow. The function is the color of the shape. So triangle maps to red, rectangle maps to yellow, Pac-Man shape maps to green, and square also maps to red. Of the two visualizations, the mapping visualization is the most common one used. Now, suppose that we are given the function y equals f of x. So in this case, the variable x is called the independent variable. And the variable y is called the dependent variable. Right, so these are so named because in this case, x, which is the input of the function, it's independent of anything. You can throw anything from the domain in for x. However, once you've chosen that x value, now y is dependent on that. So the value of y depends on the value of x that is input into the function f. To determine the domain, of a function, we must consider any restrictions that need to be placed on the independent variable. So we need to consider restrictions on the independent variable. Now, these are both mathematical restrictions, so what is mathematically permissible, as well as any physical restrictions. So if you have an applied problem, any of those physical restrictions, I can go on to it. So for example, if you're considering a particle's position with respect to time, you'd have any mathematical restrictions depending on what the function for the position is, as well as the physical restriction that time must be non-negative. A negative time does not make sense. In terms of the mathematical restrictions, there are a few rules to remember. The first is if a function has a denominator. What's in the denominator must be non-zero. Second, if a function has a radical with even index, i.e. square root, fourth root, sixth root, etc., what's under the radical must be non-negative, i.e. it cannot be a negative value. We also have functions that involve logarithms, which is considered in a future video. Now, the graph of a function f, we'll call it, is the set of all points xy in the xy plane such that x is in the domain of f and y is equal to f of x. Now recall that the xy plane is the standard Cartesian coordinate system, where x is your horizontal axis and y is your vertical axis. Now, if we are given a graph, there's a way of determining whether that graph represents a function or not. And that is done via the vertical line test. Which states a curve in the xy plane is the graph of a function if and only if each vertical line intersects at most once. So for example, if we take a look at this graph right here, this does represent a function. Right, because no matter where I draw a vertical line, I can draw one here, 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 over here. It's intersecting the graph in at most one point. If, however, we consider something like this, let's say. This does not represent a function. Y equals f of x. Right, because I can draw a vertical line here and it intersects the graph twice. And all it takes is one vertical line intersecting the graph more than once for it not to be a function. However, it is a function. X equals f of y. Right, in this case, we'd have to do a horizontal line test. So basically what we're doing is we're going to take this graph and rotate it. So that now this is the y-axis, the horizontal's y, and the vertical's x. Now it looks like this. Now we can apply the vertical line test and look. No matter where you draw a vertical line, it's only going to intersect at most once. If we were to look at something like this, now this is neither a function, x equals f of y, nor y equals f of x. In fact, this, we can say, is the unit circle, or just specifically a circle. So this is a circle. And we know that a circle has the equation x squared plus y squared equals r squared, where r is the radius. Now let's look at some operations that can be performed on functions. So let's call these function operations. First we have the sum of functions. Let's start with let f and g be functions with domains A and B respectively. So the sum, f plus g of x, is a function, and it's f of x plus g of x. The difference, f minus g of x, is also a function, and this is f of x minus g of x. Then we have product of functions. So the product f times g of x is simply f of x times g of x. And then we have a quotient of functions. F over g of x, which is just f of x divided by g of x. Now for these three operations here, sum, difference, and product, they all have the same domain. And the domain is simply A intersected with B. That is, it's the set of all elements that are common to A and B. If we look at a Venn diagram, say this is the set A, this is the set B, then A intersect B is what's in the middle. The domain for the quotient is a little bit different. So for the quotient, the domain is A intersected with B minus the set of x in A intersected with B such that g of x is not equal to 0. In other words, what we're going to do is we're going to take A intersect B from above and take out of that any elements that makes g of x 0. I'm sorry, this should not be not equal to 0. This is minus the set of all elements such that g of x is equal to 0. And there is one more function operation, and that is known as the composition. It's represented that way. F circle g of x, or f composed with g of x. And this is simply f of g of x. Its domain is the set of all x in B such that g of x is in A. Right, that is, it's the set of all elements in the domain of G that make g of x in the domain of F. We close out this video by looking at several examples. Okay. Oops. All right, let's consider the function f of x equal to 2x squared minus x plus 1. Now, f of 1. So when evaluating a function, what we do is we take the input, in this case 1, and plug it in everywhere we see an x. This then gives us 2 minus 1 plus 1, which is just 2. F of negative 2, we do the same thing. Everywhere there's an x, we're putting in negative 2 instead. We get 8 plus 2 plus 1, and so we get 11. F of A will be 2a squared minus a plus 1. There's no further simplification we can do there. And finally, let's look at f of a plus h. Now, a plus h squared, we can expand that. So there are two ways that you can do this. You can either FOIL, or you can use the formula a plus b quantity squared is a squared plus 2ab plus b squared That is from algebra. Now distribute that negative through, we get minus a minus h. Now we can go ahead and distribute that 2 through, 2a squared plus 4ah plus 2h squared minus a minus h plus 1. And there's no other simplification we can do. And so there is our evaluated function. Let's now look at this example. And so it says that Thermomaster manufactures an indoor-outdoor thermometer at its Mexican subsidiary. Management estimates that the profit in dollars realizable in the manufacture and sale of X thermometers per week is given by P of X equals this. We want to find Thermomaster's weekly profit if its level of production is 1,000 per week and then 2,000 per week. So what we're looking for is we're looking for first P of 1,000 and then P of 2,000. Now the easiest way to evaluate these is by use of technology. Specifically, TI Inspire CX2 CAS I will be using. The easiest way to do this is to first define the function P of X. So we're going to do P of X. Then we'll hit Control and then this button right here, colon equals, which is saying that this is a function that's being defined. Then it was negative 0.001 x squared plus 8x minus 5,000. Now when we hit enter, we'll see done. That means that the function P of X is now stored within our calculator. And we can now do P of 1,000. Notice how P is now bold. That's because it's recalling a previously stored function. Hit enter and we get 2,000. So that means that when 1,000 thermometers per week are produced, the profit is $2,000. Now we can do the same thing, except for 2,000. So I'm going to hit up, so I can highlight P of 1,000, hit enter. It's going to bring it back down. Now all I have to do is scroll over. I'm going to replace the 1 with a 2, and we get 7,000. So the weekly profit when 2,000 thermometers are produced is $7,000. Okay. Now let's consider two functions. F of x is equal to the square root of x minus 1. G of x is equal to 1 over x squared minus 4. And a third function, h of x is x squared plus 3. Let's look at the domain of f. Since we have an even radical, what we have to have is what's underneath of it being non-negative. So x minus 1 has to be greater than or equal to 0. This means that x has to be greater than or equal to 1. So domain That's a terrible looking D. Domain of F would be the interval 1 to infinity, including 1. If we now look at domain for G, we have a denominator, which means that what's under, or what's in the denominator, cannot be 0. So we have to have x squared minus 4 not be equal to 0. This would mean that x squared cannot be equal to 4. This means that the absolute value of x cannot be equal to 2. Which means that x itself cannot be equal to negative 2, and x cannot be equal to positive 2. So domain of G would be minus infinity to minus 2, unioned with minus 2 to 2, unioned with 2 to infinity. So everything except plus or minus 2. I don't know why the keyboard keeps popping up. That's getting annoying. If we now look domain of H, notice that it's a polynomial. X squared plus 3. Doesn't have a denominator. Doesn't have an even radical. So there's no restrictions. So the domain for H is everything, minus infinity to infinity, which is also represented this way. This means the set of real numbers. Now look at this example. Open box is to be made from a rectangular piece of cardboard 16 inches long and 10 inches wide by cutting away identical squares, x inches by x inches, from each corner and then folding up the resulting flaps. We wish to find an expression that gives the volume V of the box as a function of x and then determine what the domain of the function is. Alright, so we're going to try and draw this. We have a rectangular piece of cardboard that is 16 long and 10 wide. So let's say something like that. 16 long by 10 wide. And we're going to take from each corner squares that are x by x. Then what we're left with here will be 10 minus the 2 x's that we took away, right? So this is length x, this is length x, and then this would be 16 minus the 2 x's, right? Because this here is length x, and this here is length x. So now when we fold it together, we will get a rectangular box. Make sure the line is parallel. Looks something like this. Okay. Now this here will be x. Then this here will be 16 minus 2x. And this here would be the 10 minus 2x. Now remember, volume of a rectangular box is length by width by height. So v of x would be 16 minus 2x times x times 10 minus 2x. We're going to have 16x minus 2x squared times the 10 minus 2x. So we'll now have 160x minus 32x squared minus 20x squared plus 4x cubed. Rearranging and combining terms, we wind up with 4x cubed minus 52x squared plus 160x. So this is an equation for the volume of this box. Now, in terms of what's mathematically permissible, there's no restrictions, right? We don't have a denominator and we don't have an even radical. However, we do have physical restrictions we have to look at, right? Length has to always be greater than 0. So that means that 10 minus 2x has to be greater than 0, and also 16 minus 2x has to be greater than 0. Now, theoretically, we could have length being 0, so we'll do greater than or equal to. This one would imply that 10 is greater than or equal to 2x, which means that x itself would have to be less than or equal to 5. The second restriction says that 16 minus 2x has to be greater than or equal to, that 16 itself has to be greater than or equal to 2x, which means that x has to be less than or equal to 8. So x has to be less than or equal to 5 and has to be less than or equal to 8. But 5 is already less than 8. So we can actually really just ignore this condition because it's kind of absorbed into that condition. So the domain for our volume here is 0 to 5. I'm sorry. theoretically negative infinity. No, it has to be 0, right? Sorry, 0 to 5, right? Because we also have to have x being greater than or equal to 0 because of this condition right here. So this would be our domain. Okay. Now, let's say f of x is the square root of x plus 1. G of x will be 2x plus 1. We wish to find the sum, difference, product, and quotient. So we'll say the sum, s of x, is f of x plus g of x. Square root of x plus 1 plus 2x plus 1. There's no way to simplify that, so we'll take that as our sum. Difference, f of x minus g of x, square root of x plus 1 minus the quantity 2x plus 1. So we get the square root of x plus 1 minus 2x minus 1. The product is f of x times g of x. So square root of x plus 1 times 2x plus 1. We can distribute through, and we get 2x times the square root of x plus 1 plus the square root of x plus 1. And finally, we want the quotient as well. So that'd be f of x divided by g of x, square root of x plus 1 divided by 2x plus 1. Let's also find the domains. Now, the domain of f would have to be negative 1 to infinity. It has an even radical. Domain for g is all real numbers. Now, the domain of the sum, the difference, and the product are all the same. And that is the domain of f intersected with the domain of g. So that is negative 1 to infinity intersected with minus infinity to infinity. It's all the common elements. That is negative 1 to infinity. Domain of q. So the domain of the quotient. Remember, is the domain of f intersected with the domain of g minus any element x within that intersection that make g of x 0. So where is g of x 0? Well, since g of x was 2x plus 1, solve for x there, we get x is negative a half. So this is the interval -1 to infinity minus the set of just 1/2. So we're going to take -1/2 out of this interval. This will give us -1 to -1/2 unioned with -1/2 to infinity. Now taking a look here, suppose Puretron, a manufacturer of water filters, has a monthly fixed cost of $10,000 and a variable cost of this, where X ranges from 0 to 40,000 measured in dollars, and X denotes the number of filters manufactured per month. We wish to develop a function, C of X, that gives the total monthly cost incurred by Puretron in the manufacture of X filters. Now, total cost. Would be our fixed cost plus the variable cost. So C of X would be our fixed cost, which is $10,000, plus the variable cost. Now, if we just rearrange this, we write C of X as that plus 10x plus 10,000. Now we need a domain. Well, the domain would be the intersection of the domains for the fixed cost and the variable cost. Well, the domain of the variable cost was given as 0 to 40,000, and fixed cost has domain of all real numbers. So our domain is 0 less than equal to x less than or equal to 40,000. Now let's suppose the total revenue realized by Puretron from the sale of X water filters is given by this here, where X is again between 0 and 40,000. We wish to find the total profit and then determine the total profit when the level of production is 10,000 filters. So total profit is revenue minus cost. That is, profit function P of X is revenue R of X minus cost C of X. Revenue was given now the cost we just found rearranging and combining like terms, we wind up with this. And again, this is for x between 0 and 40,000. So this is our profit function. Now we want to find the profit when 10,000 units are produced. So again, what we can do just want to make sure that okay. So I was just checking to make sure that my profit function was correct, and it is. We come over, let's define a new p of x. So what's going to happen now is we already had a p of x stored. I'm going to replace it with this new function, which was negative 0.0004 x squared minus 10x minus 10,000. I want to hit enter. It's done. Now we have a new p of x stored. So now if I go and I hit p of 10,000, it's going to use this new function, not the old function. And something is wrong, so I will be right back once I figure it out. I'm back and I realized where I messed up. This is supposed to be 20x minus 10x. I had ignored that plus 20x, so this should be plus 10x there. Now what I can do is if I come here, I can scroll back up to here where I define my function, hit enter, because I just need to adjust this. So I scroll over, hit delete, hit plus, now hit enter. Okay, there's my new function. And I can just scroll up to the p of 10,000, enter, enter, and there we go. We get 50,000. So what this is saying is that the total profit when 10,000 units is produced is $50,000. All right, now let's take f of x to be x squared minus 1 and g of x to be the square root of x plus 1. We wish to find g of f and f of g. So we'll start with g of f. So this is g of f of x. So we get g of x squared minus 1. So what we're doing is everywhere we see an x in our definition for g, we're going to put in an x squared minus 1. So square root of x squared minus 1 plus 1. Now, f of g, we get f of root x plus 1. So everywhere we see an x in the definition of f, we're going to replace it with a square root of x plus 1. So square root of x plus 1 quantity squared, then minus 1. We can write this as x plus 2 square root of x plus 1 minus 1. And of course, plus 1 minus 1 is just 0, so we don't need it. And we can write it as x plus 2 root x. Now notice that g of f does not equal f of g. So the order in which you take the composition of functions does matter. take a look at our final example of the video. An environmental impact study conducted for the city of Oxnard indicates that under existing environmental protection laws, the level of carbon monoxide present in the air due to pollution from automobile exhaust will be 0.01 x to the 2/3 parts per million when the number of motor vehicles is x thousand. A separate study conducted by a state government agency estimates that 10 years from now, the number of motor vehicles in Oxnard will be given by 0.2t squared plus 4t plus 64,000. Find an expression for the concentration of carbon monoxide in the air due to automobile exhaust 10 years from now, and then we'll use that to determine the level of concentration 5 years from now. Now, the concentration, which we're going to label as C of t, 10 years from now, will be the composition of concentration with the number of motor vehicles. So it'll be 0.01 times, now we're going to replace x with this right here, this 0.2t squared plus 4t plus 64. And of course, that's being raised to the 2/3 power. So this is the expression we're going to be using. Now we want to find C of 5. And again, the easiest thing to do is to put this into a calculator. So let's go ahead and define a new function, C of t, which we said was is 0.01 times 0.2 t squared plus 4t plus 64. Now all raised, so I'm going to use this caret button to the 2 divided by 3 power. Now I just need to make sure that I'm out of the exponent, so I can do that by either hitting the arrow key here or by hitting the tab key. Hit enter. So there's our function stored. We now want C of 5. And we get 0.199339. So about 0.2 ppm, which is parts per million. That concludes this video on our look at functions. The next video in this series, we will begin looking at types of functions. Specifically, we'll be looking at polynomial and rational functions.